Okay, so my name is Pranav, and this is work done by me at Cornell University, and I'm going to tell you 19 things, well, ideas which I think were sort of good, and hopefully these ideas will inspire future generation of practical legged robots. So a bit about the robot in the picture. This is Cornell Ranger. It's about 1 meter tall, weighs 10 kilograms. It's a four-legged biped. The weight box. Computations on board. It's powered by batteries, which drive electric motors basically. It's fully autonomous except for steering, which you can command by using a radio controller, which this person here, Jason, is holding. So the big goal for us was, can we get this robot to walk a marathon on a single battery charge? And for that, the controller has to be energy effective, robust, and the hardware has to be reliable. And actually, we did walk a marathon. So we started in 2006 when the robot walked 0.6 miles. With our energy metric there was total cost of transport, which is energy used per unit weight per unit distance traveled. That was 1.6. But subsequently, improvements in controller design and hardware got us to 40 miles with a total cost of transport of 0.28. And recently, a month after that, we were able to show that we can get the cost of transport down to 0.19. And both these are first. So that is the longest distance walk, and that's the lowest total cost of transport ever achieved on any legged robot. Okay, so what did we learn from this? Well, we want to walk, and we just did steady state walking, and we want as few degrees as possible, and we decided that we want just 4 degrees of freedom, 1 in the hip, 2 in the ankles, and 1 in the one is the twist, which helps us to steer. We want the legs to be light, so we had carbon fiber tubes for the legs. The feet were from aluminum, they were light too. The thighs were boxed from aluminum, they were box shaped, and that's where we put all the electronics, and the batteries were attached to those boxes. That kept the legs light. What we want is, we want the legs to be light again, so what we did was, we had motors in the thighs, and these were driving the feet through a cable drive. So the red line there is the cable drive, and that is basically moving the feet up and down. And we have the springs. These springs are designed to be constant force springs. They ensure that the leg can flip up, and they maintain the tension in the cables. Now, symmetry is a good thing, because then we don't have to model two steps, we just model one step, and it's also easy for the controller. So we tried to balance the actuation by suitably tuning the stiffness. So in this case, the cables in the outer legs had half the stiffness of the inner one, so that ensured that they were symmetric. To get dynamic symmetry, it turns out that if you ignore the weight of the feet, then you have 4 parameters: the masses, the inertia, and the location of the center of mass. And it turns out that to have dynamic symmetry, you just need to match 3 conditions, as you can see down there. And it turns out that you can actually balance the legs without disassembling the robot. That was a cool thing. Now, heel strike sensor is a very important sensor, and we want that to be reliable. So the feet were designed to be load cells. So what happens is, when there's a force on the foot, a vertical force, that changes the gap in the gap you can see there on the right near the optical sensor, and the gap is proportional to the vertical load, and you can measure that gap using the optical sensor, and that was how we measured the vertical force. The feet were circular shaped, and there's something special about this design. If you take the line joining the center of the circular foot, so if you take this line, it cuts the point here, which I call the sweet spot. It turns out that if that is a contact point, then you don't need extra effort to maintain that contact point. So that's sort of an equilibrium position. And The other good thing about this shape was this allows you to do push off, toe off, flip up, and the best thing is when you model this, you don't have to worry about multiple contact things. It's just a rolling cylinder. It can be modeled as a rolling cylinder. Now, one problem we had was we have essentially a 2D robot and we wanted to turn. The first idea was let us make the feet do something like a differential rotation by servoing that pulley, that particular pulley there shown on the right. And that didn't work very well for us because it ended the 0.6 mile walk, and once the 5 mile walk was about to go out the door. So the next idea we implemented was we introduced another degree of freedom in the inner legs. So the steering motor, which drives the inner legs via the parallel mechanism, and that gives the robot the twist which is needed for steering. Coming to the overall electronics architecture, so there's a main computer which is doing the overall control and estimation. There are satellite computers which are doing local control at the joints, and these two computers, well, there are 5 of the satellite boards, and they are communicating with the main processor via CAN bus. We chose CAN bus because it's reliable and it's modular too. Now we can also log parameters back and forth in the main board via laptop using Bluetooth communication. Now all the boards, the satellite boards which are controlling the joints, were custom built. So on one particular board we have ADC module, we have motor controllers, an encoder calculator, and what this ensures is we get a small footprint, which is important, and also this kind of architecture is more modular. Now when we do these walks, we have to account for the energy going into the sensors and microprocessors, and we shopped for energy efficient electronics, and we had only 5 watts went into the electronics, and that was, I think, very important, as you'll see later on. We wanted a good DC motor model because we are going to do model-based control, and we were kind of surprised that there was no good model. So we went built our own setup and did experiments and figured out that motors are tricky to model. Basically, we found that there is load-dependent friction, and then there's a brush contact resistance, and I think that was essential in getting the model right. Now, a big lesson we learned is you cannot believe specification sheets. So what we found with the motors in particular was the resistance was twice what it is, which means that the resistive losses got doubled. The inductance was a third, and we had this nasty contact resistance which is basically non-linear. Now we tried to do model validation, and when we tried to do that validation, we found that we got a good agreement with the dynamics, but we had very bad agreement with the energetics. So we were 47% off from the energetics, and that actually made us go back and rethink what's going wrong. So what happened was we used edge bridges to control these motors, and there's a certain pulsing time you get to choose, and if you don't do the pulsing fast enough, then you get this, you don't get a good integrator action, and which means that you lose energy here. So what we did was we basically increased the PWM frequency and added some inductance. Now, we've been a passive dynamics lab. We thought that we can take passive dynamics, put it on the floor, and get it working, but we decided we're going to take a different approach. Let's use optimal trajectory control, and if passive dynamics is a good solution, let's adopt it. So let's discover it if we can. And here what I'm showing is a solution for, is an optimal, I basically solved an optimal trajectory control problem with metric of total cost of transport, and I'm showing current versus time. For DC motor stalks are proportional to the current. Let me start with the ankles. So there's this phase where there's almost zero torque, and then there's the push-off, which continues in double stance, and there's flip-up, flip-down. What was surprising is the hip is not passive. One thing is we have friction, so the motors have to, drive the legs forward. And where is a good place to put energy? Where you put energy, the best place to put energy for motors is when they're most efficient, and that's typically at fast speeds, and you see this big bulge right in the middle. Now, we as a community are we are interested in walking, and we try to solve this problem in we try to minimize the cost of transport, but we found that the electronics accounted for like 50% of the cost. So future robots will have to come up with better solution to this problem. Can we get more efficient electronics? Can we do that? And in our case, we found that the flip-up, flip-down, which is just preventing stubbing of the legs, accounted for like 25% of the cost. Which I'm going to?
You go down.
Okay. I have three more slides to go. So what we do is, to implement this, we have a trajectory generator, and we stabilize that particular trajectory. And the idea is to take the optimal solution, this is our optimal solution, and approximate it. So the structure is chosen by us, but the amplitudes are chosen by the optimal software. So what we achieve there is we reduce the cost of we increase the cost of transport by doing that by 7%, as you can see there, but we reduce the parameters by like a factor of 8. For stabilization, what we do is instead of trying to track the trajectory completely, we try to track key points in the trajectory. And the idea there is to linearize the system and use some kind of a linear regulator. To implement this particular architecture in the robot, we use a finite state machine that works well for us. And this is just showing one particular the hip state machine here.
We should wrap up so we can have time for questions and going for lunch as well.
Okay. Okay. So we did not do a very good job on estimation, but we found that the push-off time is kind of crucial for stability as well as energetics. And the last thing I would say is testing is like vital. So every time we have the robot going, we used to collect parameters. When the robot falls, look at the data, fix bugs, go on. And it was kind of exhausting, but I think that actually got us this record.
Okay, so
thank you.
Questions?
I can take questions, yeah.
Yeah, go ahead. Yep.
Okay. So for experimental evaluation for the cost of transport, did you actually measure the voltage and the
Correct, that's right.
For both overhead and also the motion?
Yes.
Separately?
Yes.
Okay. How about in the simulation? What kind of model did you use for the overhead?
So the overheads is not, we didn't model that. So what we did was we had the robot on the bench and we found what the overhead is, just the measuring, and I put that in the simulation. So there was no models for overhead.
How about the motion portion? Did you use still use the integration of the?
Yeah. So for the other costs like motor cost, I had this motor. I spent a lot of time getting a motor model. So that was built into the simulation.
Okay. It was the heat considered in the model?
So we had like we kept an estimate of the temperature in the windings, and we had like a controller which always ensured that we were not overheating the motors. But that was not modeled. But we did take care of that when we designed our motor control board. Yeah.
Okay.
Yes, go ahead.
You showed that the model agreed reasonably well with reality, but you showed sort of steady-state comparison. I'm wondering to what extent, how accurate would it be to say you tested the model through the reality for small point of visual experiments? How well would sort of transients to steady-state be captured by the model?
I wish I had a good answer for that. So for testing is the best way I can check this. I did not really do careful experiments on that particular aspect. Yeah.
So you showed that you had a lot of problems with DC motors, and some of them seem to be a function of the contacts.
Function of what?
Due to contacts.
Yeah.
Communication. Did you look at brushless DC motor?
Okay, so after doing this project, if you were to redo this whole project again, we will abandon brush DC motors and go to brushless DC motors. That was the conclusion. They are difficult to control, but they don't have this parasitic resistance, and basically we would have got a better, energetic with brushless motors. So we don't advocate using brushed DC motors. Basically, that's the message.
The last question?
Yeah.
I saw your percentages, but I'm wondering, based on the mechanical work of the actuators, what's the cost of transport just on that mechanical work?
It was 0.04. So mechanical, yeah. So mechanical cost of transport, which is the mechanical work done divided by energy used by piston stable, was 0.04.
Okay, I get to tell you how to get to lunch. Okay, so